It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 108, where today we have quite a special guest with us from the States. We have George Hrabovsky. George, you want to introduce yourself to the podcast? Just say hello.
I'm the president and founder of Midwest Area Science and Technology. We're an amateur science organization that promotes scientific research without regard to credentials. Some of our people have multiple PhDs. Some of our people have no degrees like myself.
That's definitely going to be a conversation that I'm sure everybody that is listening will be like, I really want to know more.
I might call a professional amateur scientist.
Perfect way to sum it up.
Awesome. So, this is going to be an awesome episode. This is the first time we have a guest in a long time.
Yeah, it's been a while, eh?
Yeah,
it's been a while for a guest.
We do have some interesting ideas for other guests coming in the future, so you should look forward to that. Before we do get into the podcast, if you are listening to this anywhere, make sure to follow the podcast, subscribe, and leave a comment down in the YouTube video.
Why would you leave a comment? Because you might get chosen as comment of the week. So this week we have Sylvia and her lovely comment. She says, thank you guys. Because of you, I'm not just learning about the things that you say on your videos. I choose this channel because it's quite interesting. I also follow you on Spotify where I started. Gracias. She says she's Spanish. So she's learning English as well, and she's learning science. So thank you, Sylvia. And you're welcome.
Thank you so much. So if you want to be next week's comment of the week, make sure to go to the YouTube video of this episode and leave a comment down below. Other than that,
I think that's basically it. I think we can get straight into the podcast. So I think we can begin, George, with the question that I've been waiting to ask you. How did you get into science? What led to where you are today?
When I was in elementary school back in 1965 and 66, NASA was launching the Gemini program in basically the lead up to Apollo. And that's really what got me interested in science. What got me into physics and math was two things. One, in first grade, the school I was at had what they called the new math. And the new math was just the old math with elements of set theory thrown in, no pun intended. And so in first grade, we were sitting here learning about sets, elements, union, intersection, all that stuff, and then we got into the properties of numbers, like the associative properties, commutative properties, and that was fascinating. And then we went into basic arithmetic, technical arithmetic, and it sucked from there on out. It was really boring, because we did the same thing in second grade, the same thing in third grade, and so I ended up hating math, which is very ironic how things turned out. But I was very interested in chemistry. And so one day when I was 12 years old, I was reading a college textbook on chemistry, chemical principles, and I got to the chapter on the gas laws. And at that moment, I realized what physics was. I realized what you could do with mathematics. It was love at first sight. And the next thing I did is I went out and bought two books. I bought a book called Advanced Algebra and Calculus Made Simple, and I worked my way through it. I remember feeling terribly disappointed when I got to the end of calculus, and that's essentially differential calculus. This is what people are afraid of? Because I worked my way through it, and it seemed easy.
Yeah.
Integration was a little harder, but, not bad for 12 years old. And then I got the Feynman lectures on physics, and that's where I learned physics.
The fact that you just mentioned 12 years old, I think, is what's baffling most people right now. Because even if people figure this out, I feel like they're doing it at least 16 to 18 years old. I don't think anybody is really doing this or even figured it out at 12. So that's just insane.
This book?
Gravitation? Wow, that's a
14. By 15, I was working my way through it.
Wow. That looks like a very thick book.
It's
But
aptly named. It's aptly.
yeah.
Articles are attracted to it as it goes by.
so. Yeah.
I think one thing that's interesting, you said you were learning about some basic elements of set theory in the first grade, and that's very different, I guess, to what we grew up with.
I grew up very different from you, though.
Yeah,
I
I know.
grew up in India. So
Some abandoned new math because
Yeah, I think
yeah, I think
that's a shame though,
set
because
theory was not taught to us.
I've thought about this before, and I think I've said this before on the podcast, that I think math should be taught using set theory first. I think it builds.
and once you get past basic calculus, everything utilizes set theory. I mean, even
Yeah.
Yeah.
when you start with linear algebra, that is all written in the language of set theory, particularly if you get into vector spaces, right? I mean, there are the
Yeah.
two approaches. You have the matrix approach and you have the vector space approach, but they're all equivalent.
Yeah.
And with set theory, you can show that sort of thing.
Yeah, and I only got into set theory in the first year of university, where we were forced to learn about proofs, and proofs, essentially boil down to the most basic, bare bones elements of logic. And so obviously set theory comes in there. So I was kind of forced introduced to set theory that way. But then through linear algebra, I got to see how awesome set theory was. And then I was inspired to, think about how learning set theory earlier on would have been so much better to build up kind of the skills and the knowledge that I use today.
So, would you say that the set theory that you learned in that first grade, because I don't think usually people even really remember too much that they study or learn in first grade, or they just maybe put it at the back of their head and they just take it as a given. But my question to you is, did you take the knowledge that in first grade and did it actually help with your understanding of the calculus books? And did it actually help with your understanding of the advanced stuff?
Really, no, because the calculus book wasn't written in a theoretical way. It was written in a practical way. This is how you calculate a limit. This is how you calculate a derivative. This is how you calculate an integral. It wasn't, the formal definition of limits where you have the epsilon and deltas, the Weierstrass notation. It wasn't that at all.
Yeah.
So, I mean, you have the two levels of calculus, one the practical level and then the other the theoretical. Now, if you have the practical and you learn the theoretical becomes much more understandable.
Yeah.
But I'm not sure that's where you want to start.
So would you say, no, but you wouldn't want to start at the theoretical either, though, would you? Or because I feel like that might be a little too much, because that might, what do you think?
Practical and then go into the theoretical, but
Oh,
always,
sorry, I thought you said.
but
the other
always
way, right.
remember that you're spiraling back. You're spiraling through the material over and over again at ever increasing levels of sophistication.
Yeah.
And
I mean,
that's the thing that a lot of professors have trouble grappling with their students, because they've reached a level of sophistication and they don't remember what it's like not to know any of this stuff.
That's such a perfect way to put half of our teachers here. I guess I shouldn't be saying this being in the school.
Because the story is always the same, right? In high school, it's, this is what a limit is, calculate limits. This is what a derivative is, do derivatives, and, dot, dot, dot. Next thing you know, 1 year later, you're doing the exact same thing, but a little bit more complicated. The next year, you're adding dimensions and, abstracting your what is allowed to be a domain.
See, that's not the way I did it. I did it. I learned the basics, and then I got ever expanding books. I mean, advanced engineering mathematics books, and then I got into the actual theory of calculus, real and complex analysis, functional analysis, differential geometry, all of that stuff.
So, if you don't mind, because I think, again, a lot of our listeners are going to be very intrigued with you, because as I mentioned, a lot of them, I think, are either in school, doing a physics degree or thinking about doing a physics degree, and now all of a sudden they're hearing this individual with no degree literally doing flawlessly in physics. So I think a lot of people. Sorry, I can't read that.
The theoretical minimum.
Oh, that's exactly the book. By the way,
Under Lenny Suskind's name.
we should probably mention that the book written by you, George, the theoretical minimum, co-written by you and Leonard Susskind.
2 drafts. He wrote the 3rd draft, and then we hammered out the 4th draft.
Wow.
Wow. So you worked personally with Leonard Susskind. Wow.
Well,
I mean, you've also worked. Yeah.
because I'm a relativist and he's a particle theorist. Normally we would come to blows, right?
Mm-hmm. Yeah.
All you have to do is to get a relativist really annoyed is mention ADS CFT, right?
What is that?
Sorry, we're not too.
De Sitter space and CFT is conformal field theory, which is a way of doing
Are those like
string theory with black holes.
Right.
Oh, okay.
That's what I thought.
Sorry.
Okay.
The reason why it makes relativists crazy is it has nothing to do with reality. It's just a mathematical structure to allow you to prove theorems. So we don't live in ADS. And the thing that ADS allows you to do with string theory is it allows you to turn off gravity in the black hole. And then you can use a conformal transformation to go from inside the black hole to outside the black hole. And that's where you get the firewall on the event horizon and stuff like that, where strings build up on the event horizon.
Oh.
Wow, that's a very interesting way to explain it.
So that makes relativists nuts. Because it does...
So the fact that you got together is crazy to begin with.
I'm sorry?
So the fact that you got together is pretty crazy to begin with.
Well, I was listening to his Stanford lectures, and I'm like, that's actually a really cool lecture. And I checked it out to see if there was a book, and I emailed him and said, you might remember me asking you a question when you came to Madison to give a colloquium on your information theories, black hole stuff. And I just listened to a couple of your lectures on mechanics. Would you be interested in turning this into a book? 'Cause I think it's a terrific.
Wow, that's how it
I think your
started.
lectures are terrific. And he said, I've had lots of people ask if it was a book. You're the first person who asked me about turning it into a book. And go ahead and write a couple of chapters and see where it goes. And we talked a little bit about philosophy and stuff. And we were all right on the same page. And so I wrote the first 3 chapters and sent it to him. He paid me a great compliment. Not that I need compliments, but it was, he said, I've known a lot of amateur scientists. You're the first one I've met who knows what he's talking about.
that must be such an amazing thing to hear.
Highest form of compliment.
A lot of amateur scientists are crackpots, to be perfectly blunt. I get letters and emails from them all the time. They think that I'm going to be sympathetic towards them because I'm an amateur scientist. No, I am not sympathetic towards them at all. If I think they're full of crap, I will use even more base language than that to tell them what I think. As a Navy veteran, and my service in the Navy started when I was 17, and it basically, that's where I learned to teach. And it has informed, the attitudes that I got there have informed my life. It's given me a lot of self-confidence and a lot of drive. And that's one of the ways that I've always had the drive. That's why I was able to stick to a problem until I could drink its blood, right?
Yeah.
I really want to focus on that drive because I think, as I was mentioning before, I think that's what everyone is so curious to know. How, at 13 and 15 and 16 years old, did you... Well, first of all, the fact that you even went out and bought the books itself, I think is amazing. But second, I really want to know, if you don't mind sharing, like, not obviously in detail because I don't even know if you remember it, but briefly, like, your study pattern. Like, how did you even, I can't imagine a 13-year-old learning like Feynman's lectures. Like I can't imagine that. So
Which is available for print on demand from Lulu, from the MAST website, called Self-Instruction and Teaching, Science Education for the New Millennium. And that describes how I went about it.
oh, really?
So a whole book. Wow.
Do you want to briefly summarize it for us, if you don't mind?
It was all critical thinking, right? You come up with you are confronted with an idea, and you have to ask yourself, why should I believe this? You know, is this idea based on a fact that was acquired observationally or experimentally, or is it based on a conjecture? If it's based on a conjecture, what are the fundamental assumptions of that conjecture? Where did it come from? Why should I pay any attention to this at all? Mm-hmm. And then, once you get that, you can start to go, well, how does this relate to other things that I've learned? And that's the pattern of study. It's a lot, you never read a book, unfortunately, from cover to cover. Like, if I was going to take this book and analyze it, okay, what you need to... I am not responsible for this title or the subtitle. What you need to know to start doing physics. This was a marketing department. Both
Oh, really?
subtitle.
Really?
It should be theoretical
Wow.
minimum classical mechanics. That's what this is. It's a book on classical mechanics. We cover effectively all of classical mechanics in 240 pages. We start with a dynamical system, with a diagrammatic approach to dynamical systems. Okay, almost graph theory.
Wow.
And then we talk a little bit about coordinate systems, vectors, and some trigonometry. Then we introduce calculus and kinematics. Then we introduce integration and some dynamics. Then we talk about multiple systems and partial derivatives and things like that. And then we go into Lagrangian mechanics. And then we go into Hamiltonian mechanics, and then Poisson brackets and canonical transformations. In the appendix, we do celestial mechanics from the Lagrangian approach. All in this.
So basically, literally the Susskind lectures, like covering the Susskind lectures, but in a textbook.
I wrote the first volume, and I took his lectures as an outline, and I rewrote them.
Right.
And it was, I'm a very fast writer, and I started in September, and by January I had written 150,000 words.
Wow.
Wow.
And then
But this is not even in your field. I'm so confused as to how, like, okay, I understand that you've read books on it. Like, I understand that. But, like, this is Leonard Susskind we're talking about. Like, he probably, like, he has, like, I guess so. I guess that's the approach you got to take for everything.
Yeah.
That's such a beautiful way to think about it.
when people sweat, because they know I'm going to ask basic questions. If I don't know what something is, I'm going to ask. And they better be able to answer, right?
Wow, that's such a nice way to tackle things, because again, we were talking about this before the podcast, but I think the most common thing that with people, or at least with me, literally before today, was thinking that, to actually get anywhere in science, we were literally talking about this last night too, like to get anywhere in science, you would like need some credibility, and that's why we do school. Like, why are we in school is basically what the conversation was last night, and we're like, well, so that we can be in science. But now we're literally learning. That's
It's
not
certainly
needed.
one way to do it. But you have to understand that these degrees have only been around for a couple of 100 years. And people have been doing science for thousands of years.
Thousands and thousands.
So there are many pathways to reaching an objective. I took what was the low energy curve.
I mean, it worked. Right.
Yeah. So you were presented with, at any point in your life, you could have made the decision to go to school. right? So what made you stick to just self-learning?
Well, part of the reason was the school system. The school system was so slow and so boring. I mean, I wasn't only interested in math or science. I mean, for example, by the time I was in third grade, I had memorized, for example, all the battleships that got whacked at Pearl Harbor.
So you just like to do that kind of stuff, basically, like just almost an obsessive personality, right?
I studied, you know, I'm a professional writer. I write. I've written for newspapers. I've written for magazines. I've written short stories. I write horror stories. I write fantasy stories. I write science fiction, rarely. But, I write spy stories. And I also design fantasy role-playing games.
There's just so much creation.
Yeah, just from where to where. I think the perfect word for you, I think you just said it, would be creative. Like, you're just so creative.
Again, you have to remember that I started doing that stuff when I became impatient with school. So I started learning on my own. And I saw no reason to stop. I didn't do it all myself. I would walk into a professor's office and start talking to them at the University of Wisconsin in Madison.
And were you a student of this university, or would you just walk in? Wow. Wow. What would the professors think or say?
Well, some of them would say, well, I don't know how to answer that question. Why don't you go talk to this person?
No, but I'm saying, like, they would actually talk to you. Like, I don't know. I would just think someone not even in this school, I feel like, would you not even bring that up? Would you just be like, hey, I have a question? Oh, okay. Yeah.
I have never had anybody ask me if I had a degree.
That's almost a compliment, I feel. That's almost a good thing, right? Because they're like, oh, it's almost like people probably already understood that, okay, this guy probably has a degree, which is why he's talking to me.
Physics department at one time when I was 13, and somebody asked me, what's the integral of sine x? And I told him, cosine x, and he said, well, he knows his integrals.
That's hilarious. That's hilarious.
Funny. That's especially funny because, like, at the beginning of the semester, when I had to evaluate my first integral after the whole summer, I was like, I forget how to integrate. I don't know. I had to refresh my memory.
I learned computer programming when I was in high school. I built my first computer when I was in high school, an IMSI 8080. You think programming is hard now? Try machine code with hexadecimal language with toggle switches on the front.
I was just going to ask you how, like, when you say built computer, it's very different from people saying I built a computer today. Yes, exactly. Like, you actually built the computer.
2-year paid appointment at the physics department at Madison at the University of Wisconsin. And I never told anybody that I was an electronics technician because I didn't want to get stuck doing experiments.
Wow, so you really thought of...
The department Mathematica guru.
Right. I don't actually think we've spoken about the Mathematica part on the podcast. Maybe talk, because I know... So, I mean, Mathematica, for those that don't know, yeah.
This episode of the podcast is sponsored by Brilliant. If you liked all of the things that we spoke about in this podcast so far, which is actually a lot, then you're definitely going to want to check out Brilliant to get a more in-depth look at each one of these topics. So far, it's hard to put into a single box what we've been speaking about. Right? We've been talking about physics, math, scientific thinking in general, computer science, and more. If you head over to brilliant.org, you can find courses on every single one of these topics. And the first chapter of every single course is free to just go and try out. And if you want to continue on and go deeper into these courses, you can use code MPP for 20% off of your premium membership, or go to brilliant.org/MPP for this offer. So go ahead and have fun learning with these interactive courses, and let's get back to the episode.
For people who don't know what Mathematica is, Mathematica started out as what's called a computer algebra system back in the 80s. Steve Wolfram is a genius. He was very much like me in some respects, except he was actually publishing papers in Phys Rev when he was in his teens.
Wow.
In particle physics. And so I was just doing black hole stuff, and he was doing particle physics. Is basically the divergence. And I was also doing stuff in biochem. I had my own biochemistry lab. I was doing my own research in protein structures and bacteria with my own home laboratory.
Where did this come from?
Where did that? That's completely different from what we've been talking about. Where did the biology? Where did that come from?
I did mention that I was reading a book on chemistry when it started, right?
Yeah.
Right.
Yeah.
You did.
Very interested in biochemistry, and particularly bacterial biochemistry. So I was scrounging equipment from the city health department and from the university biochemistry department, and I had professors there who would give me stuff, and I'd bring them home and set up my lab. I had my own paper chromatography rig, and I was able to use solvents to break up cells and to get the amino acids out and figure out what proteins were there.
That is yeah.
Can't even imagine.
Oh my god.
Like, wow.
Yeah.
I don't know the amount of
So, yeah. The only thing I'll say about my military service is I had planned to go into the Navy to become a meteorologist. Again, I was doing numerical modeling of thunderstorms at the physics department. We were doing it remotely on a CDC 7600 in Colorado, and it was in Fortran.
oldest language known to man. Right? No, I just make a joke because it's so old. Yeah, but, no, I'm joking. Sorry. No, it's just a modern joke because in our class every time, because our teacher used to code in Fortran, so she's always like, "Oh, I'm so old," because it's just a joke. Sorry.
Well, I've learned Fortran, Basic, C, C++, and stuff like that, and then I found Mathematica, and I never looked back. As a programming language, is superior to all of them. And
Wow.
It's not really a. Is it really a programming language? Is that the correct?
And I've
really?
written programs to support my role-playing games with it. So it's not just mathematical. You can do text.
Could you, if you wouldn't mind? Sorry, but if you wouldn't mind, could you go into detail in some of those? Because I just want to know what programming Mathematica looks like. Like, what did you do in relation to Mathematica? Did you add some functionality?
Let me bring up a program for you, and I'll show you what it does. So in my game system, there's something called pre-adventures, so you can have adventures before your character starts out. Yeah, let me get over there. I gotta find my cursor. Oh, it's stuck.
I should mention that majority of the listeners of this podcast, as you mentioned, listen to the podcast and don't watch it. So if you can explain it, that might be a little bit better for the listeners. Right. Yeah, for sure.
So the thing is, I've heard of Mathematica, of course. I've actually never used Mathematica myself.
It's very expensive. It comes with the school, though.
Oh, really?
Yeah,
Okay, yeah. So I only use Python.
If you'll let me, I'll share my screen again.
It's very different.
So
Yeah, you
see
can go
what
for
this
it.
program looks like.
So my understanding, unless before we're going to look at the program right now, but my understanding is that Python is more of an actual coding language. This is more of like a math language.
This is what Mathematica code looks like.
A lot more words than I was expecting.
Well, what this
I
does,
thought it was mainly gonna be,
so
like,
let me
equations
run
and stuff.
this, and I'll show you what the product looks like.
So for everybody listening, we're just looking at a piece of code here.
quite an extensive program, actually.
Yeah,
that's
quite,
quite
quite long, quite
That's
long.
quite excessive.
I will put an input of 5 in here. It says, so your pre-adventure is about a monster hunt, an organized effort downtown to destroy a dangerous monster. You get a good thing, you get a bad
Oh.
This is part of your game. That's why. Okay. Sorry. I thought this was like a math program. Okay, that makes sense.
thing. No,
I mean,
really
it is
cool.
mathematical.
No. Yeah. I was just gonna say that it's really cool that you actually implemented Mathematica in your you're actually using a
But
mathematical
it's
model
a
for the game.
full-fledged generic programming language. The neat thing about it is, if you look at Fortran or C or Python, those are all procedural languages. And you
Right.
can do procedural programming in Mathematica. But if you look at Lisp, for example, that's a functional language, and you can do functional programming in Mathematica. You can also do rule-based and transformational programming and modular programming. You can do all of those paradigms all at once in one package.
Wow.
The most impactful paper I ever wrote that got published in a journal was a paper I wrote on solving the diffusion equation in Mathematica using built-in method, my own procedural method, my own rule-based method, and my own functional method, all in the same, and got exactly the same results from each method.
Wait, that's actually very powerful. That's literally what we're learning right now. Actually, solving these equations.
Partial
computer.
differential equation like the diffusion equation, but I showed
Right.
how to do it in 4 different styles of programming, all into Mathematica. And that's built
Wow.
into Mathematica. No other programming language does that.
Wow.
There is actually something similar to Mathematica, like a Canadian version of that. It's called Maple.
It's called Maple, but the
Yeah.
Maple is more traditionally a computer algebra system where Mathematica
Yeah.
started. That Mathematica has, you can actually write applications in Mathematica that don't require you to have Mathematica running. You can compile it.
Oh.
My knowledge is that Maple was actually written by a bunch of Waterloo students, like from University of Waterloo in Canada, and and we used it last year for some like research because we were like solving a bunch of PDEs. So like when you said the word Mathematica, I knew what you meant, but I had no idea that it was like actually, because I guess like the only level of code that I did was just putting in the PDEs to solve. Like I didn't actually.
There are 3 levels of use of Mathematica. One, you can use it as like a 5,000 button calculator.
Yeah.
Right.
The other thing is that you can use it as a scratch pad. You can open up a Mathematica notebook and you can do a calculation. And third is you can develop an entire programming system based on it. Are you familiar with Wolfram Alpha?
Yeah.
Of course.
Wolfram Alpha is a 10,000 line Mathematica program.
No way.
Wolfram Alpha is a Mathematica program. That makes so much sense. Yeah, of course it would be.
Was typeset entirely in Mathematica.
Oh, wow.
What? How can you write a book on what? How does that make sense?
Those people who are watching, let me pull up a
Wait, this is very interesting. I didn't actually.
Wait, it was typeset in Mathematica. I don't
Mathematica.
understand how that's...
documented the PDFs to basic books, and they were typeset in Mathematica, and they used the typesetting that I said. I'm the first author at Basic Books to typeset their own book.
Wow.
Wow.
Wait, why did you do this?
Yeah, that's a good question.
Because Mathematica is so much easier to use than tech. I hate tech.
Really? I love tech. No way.
80s technology, and we're using it today. So here's a lecture. Here's a system I'm preparing. This is again entirely in Mathematica, and I'll share my screen.
Wow, this is pretty sad because I think everyone knows on the podcast how much I love my LaTeX. So the fact that
So, for
You're saying it's
example,
old
let me make this
technology.
bigger so you can see it.
Yeah.
By the way, for the listeners out there, I believe we're looking at just a copy of the text right
Yeah,
now.
just a PDF.
Yeah, but
And
it looks
this
very
is-
different from
This is
something
not a
on Word or
PDF.
something.
This is a Mathematica notebook live.
Okay.
Oh, okay. Mathematica notebook.
So
What's
you
the
can see
advantage
the
of something
typesetting
like?
here.
Oh,
It's beautifully
Yeah.
So you can
typeset.
easily do a lot of stuff.
And the
is
nice
what
thing
I'm
is
seeing.
you can do your research in a Mathematica notebook. You can then take your Mathematica notebook and turn it into text like this. Let me show another example of something
Wow.
that I presented just a couple of weeks ago at the Midwest Relativity meeting.
This makes me want to get
Yeah.
Mathematica.
Mathematica. No, it's like
Getting Mathematica, there are 3 versions of Mathematica that you can get. The first version of Mathematica you can get is if you're a student, you can get an academic version. And that's like $150. And most schools have that. The second version is the academic and professional version. And yeah, this is the one I wanted.
yeah, I believe the other one is some $600 to $900 or something, right? The full version, isn't that something like that? 5 to 9.
Version is like $3,500.
Oh wow.
And then there's the
Jeez.
hobbyist version, which is about $300. The difference is that you can't buy it using a company card or anything like that. You have to use, and you can't use it to make money. So since I
But it's the exact same.
No, I'm assuming it wouldn't be exactly. 'Cause
yeah.
that's
So
the difference, right?
anyways, this is the paper I presented at the Midwest Relativity meeting.
Wait, why is it so expensive?
I'm assuming Wolfram did a lot
It
of work.
does everything. You know, I mean,
It's
I
the
can
only
take-
one that exists.
I can take
don't
a
know.
PDF, import it into Mathematica as a Mathematica notebook, manipulate it, and then save it as a PDF.
Wow.
So like this
Like
is.
I remember. Yeah.
Can you see
Wow,
this?
that's-
Can you see the screen?
Yes.
Yeah,
you,
yeah.
we can.
So it has
By
a
the way,
built-in
yeah.
slideshow system.
Oh, that's cool. Yeah. By the way, for the listeners out there, we're currently watching a presentation that
And so,
George presented.
So I talked about the Schwarzschild metric for the black holes. I introduced the Kruskal-Zekeres coordinates. Here's the program that I wrote to calculate the Kruskal diagram, and that's the output.
Wow. That's I don't think we understood much of that, but that looks pretty cool.
But
And all of this was from Mathematica, right? All of this. Was from
this
Mathematica.
this is the entire program to generate this next diagram.
Wow.
That's a pretty confusing. Wow. Okay.
And then I talk about what a Penrose diagram is, and here's the Penrose diagram. Here's the program for generating a Penrose diagram for Minkowski space. And there it is. And then the Penrose diagram for Schwarzschild space-time, and that's this.
By the way,
that space-time. You can see that space and time are beginning to accumulate. This would be the event horizon. This upper.
we see that.
this
Oh, that's
upper
a
left-hand
really
corner.
cool graph. Or not graph, plot.
Yeah, that is a really cool plot.
Wow,
And
that's
then,
so
and
cool.
then you can look inside the black hole, and the event horizon is now in the lower right, and that hyperbolic top is the singularity.
This is insane.
Oh my.
Wow, this is crazy. And sorry, does this conform to what theory? Sorry, I'm not sure. If
This
we're
is
too
general relativity.
familiar
This
with
is the
This is
Penrose
general relativity. Okay.
This
okay,
is the
okay,
Penrose
you're right.
diagram created by Roger Penrose. But there's
Wow.
Wow.
now you can calculate the Penrose diagram. You don't just have to draw it by hand.
And that was a function that you derived on Mathematica,
Yes,
right?
that is correct. Yes. And so this
I'm
is
really Sorry.
these are the coordinates for the different plots in
Wow.
Schwarzschild geometry for the static black hole case.
For the listeners out there, it's basically a lot of hyperbolic sines, cosines, and tangents. So it's not much that we're really watching and learning, but I think it's cool that
Yeah,
we're
it's
looking
very
at the
cool
plots.
that
Yeah.
you can do this all in Mathematica. I think that's the takeaway right there.
Yeah.
Mathematica less than a second to produce those diagrams.
Wow.
Wow.
Wow. So it's very, very fast and very useful. All right.
Okay.
the two
Yeah,
Xeon
the hardware is an
process.
important piece there.
Right.
Couple of seconds to do it on a regular laptop.
I have a very interesting, or not, or at least interesting question to me right now, which is based on all of these talks that you give. So I know we haven't really gotten into your Midwest science quite yet, and I'm very interested to get into there. But before we do, I just want to know a little bit more about when you give these talks, like when you go and present or when you go and teach or whatever, because you were talking previously about all these, presentations or papers that you've written. My question is, as an amateur scientist who doesn't have, or at least my understanding, who doesn't have access to, multi-million-dollar laboratories and universities and multi-million-dollar telescopes and stuff like that, how do you do it? Like, do you borrow other things? What's that process like of writing a paper? Okay. Exactly.
In May, I taught a 20-lesson course on basic electronics, and I put together a kit that included a dual trace digital oscilloscope for $300 for $150 that people can buy off Amazon. So for
That's
like
actually pretty cool.
$350, everybody had a nice electronics kit, and they were able to follow the experiments and stuff.
Oh, very cool.
And I taught it over. It was through MAST, and I taught it over Skype.
Wow.
And
what about the higher levels? Yeah, I'm mainly
in the
interested
last
in, for example, that
15
gamma
months,
ray burst.
In the last 15 months, a year ago, I taught a 20-lesson course on general relativity through MAST.
Wow.
Mm-hmm.
In December, I taught a 6-lesson course on programming and Mathematica. In January, I taught a 20-lesson course on mathematical methods using Mathematica. And then I taught the electronics course. We have a course that's underway right now being taught by our resident mathematician on asymptotic methods using Mathematica.
Are any of these courses still available?
We're only beginning to start playing around with experimenting with recording video and stuff. I'm thinking about the next set we do are going to be put on our YouTube channel. The only YouTube thing we have right now is a storm chase that wasn't that great.
Okay. Yeah, so how many people are participating in these courses?
Ranges from 3 to 7. So it doesn't overburden Skype.
Right.
But I mean, we don't really have enough people to have buying a copy of Zoom worthwhile.
Yeah.
Right. Oh, right. I keep forgetting this.
Yeah.
I keep forgetting that this is the school account, which is why we have Zoom for free, and without that wouldn't even be a thing. So that's definitely like a bottleneck.
I have a client version of Zoom, so if somebody else starts a call, I can link up to it. But but like I said, Skype is free, and it's got.
Let's talk a little more about your clients. You mentioned client, and I just thought about, like, I know you were mentioning that before you were doing currently what you're doing, you were a contractor physicist. And I would really love to know, like, some crazy things. Has anyone ever told you or given you a crazy contract well, again, when I say crazy, in your opinion?
The strangest contract I had was applying group theory to mythological type analysis, where you basically you basically convert the idea of an archetype into an object, and you assign relations between them as a mapping. And from that you can sort of build symmetries, and that of course leads you to group theory.
Wow.
Wait, is this part of a game? Like, what is the mythological creatures here?
He was turning his PhD thesis into a book, and he wanted me to help him with the Mathematica to do that. So this was all done in Mathematica.
Oh.
And so he had some ideas about the symmetries between different mythological types. Interesting.
Is that like
Interesting.
Wow, that's pretty cool.
One of my hobbies, because I'm a game designer, is I study comparative religion and comparative mythology.
So you were almost like a specialist.
A translate biblical Hebrew and Aramaic texts.
Wow. This is so crazy.
Just the sheer number of things that you
Studied about a dozen languages.
Of course you
Wow.
have.
So
What?
which languages
amazing.
do you speak?
Well, speak.
Or write or read?
Since I've done anything with any of them, but I've learned French, Spanish, German, Latin, Greek, Arabic, Hebrew, biblical Hebrew, Russian.
Wow.
So.
Wow. And then how many
The only thing I'll say about a lot of that is the military. So
Oh, right. That probably, yeah.
you shouldn't be talking about.
Sure.
But I really want to know, maybe, I mean, not, we don't have to focus on the language part, but I really want to know, like, deep down, I guess maybe it might be a simple question, but why? Like, why do you just enjoy doing all these different things? Like, why do you do, because usually when I talk to a scientist or a professional or something, they'll be like, oh yeah, but I've been doing this for 50 years. Or, you know, I mean, I go to work and I do this for 50. But you do like 16 different things in a week. So, like, why, if you don't mind me asking?
Interested. When I get
That's-
interested in
yeah.
something, I focus on it and I ask, is this something I really want to do? And if it is, I throw myself into it.
Wow.
Yeah, that obsession I feel is such a trait to have as a scientist. You know, that sheer obsession, that sheer passion for wanting to do something or needing to finish something or anything like that.
For example, those people in academia have this tendency to be very derisive of normal people.
Yeah.
This book was written for normal people, and we've sold in the United States over 200,000 copies of it. It's a New York Times bestseller.
It's very
And there are
impressive.
1,000 equations in here. I know because I wrote them all.
Wow.
The fact that 200,000 people will pick up a book with 1,000 equations really shows that you've almost done what you wanted to do, which is like almost like spread this love or spread this understanding to everyone else.
That was the thing that was so remarkable with working with Lenny, because even though we're from completely different camps, we had a single vision that worked in this case.
Yeah. And so is the theoretical minimum, is it a book made for people who aren't really thinking about physics on the day-to-day?
Look at this, it's classical mechanics for people who don't want to go to school.
Wow. So is it, I guess my question is, for somebody who's already studied classical mechanics, would it be kind of like they've already seen everything that's in the book, right?
Don't take my word for it. Another friend of mine, I don't always like to name drop, but another friend of mine who actually wrote the review on the dust jacket of the hardcover version is Sean Carroll.
Wow.
Sean Carroll?
Wow.
What? That's insane.
We've corresponded many times, and he wrote that almost on every page he encountered a revelation.
Wow. Wow.
So someone like him can appreciate that I'm sure that anyone can. Because I'm sure he doesn't really think about the classical mechanics that he learned when he was in university anymore. Right.
I mean,
Or
I
was
bought,
he?
there's the classical mechanics that you learn and it boils down to one thing. You're creating an equation of motion. That's what you're doing in classical mechanics. You're either creating an equation of motion or you're solving one. Now, the other thing is, in all of physics, there are only two problems with an exact solution, right? The two-body problem and the simple harmonic oscillator. Everything
Right.
else is an approximation.
Right.
So that's the thing that you have to think of as you're going through this. These are all the Lagrangian method, even the Newtonian method. We teach the Newtonian method first because to derive it is fairly simple. But it's the most complicated way of doing mechanics.
Yeah.
If you're willing to accept the Lagrangian method, you could teach a monkey to do it. You turn 3 cranks and you have an equation of motion, right?
Yeah.
You take a partial derivative, you take another partial derivative, and then you take a derivative of a partial derivative, and bang, you have your equations of motion. It's just that simple.
Yeah.
You add this, so you subtract that. Boom. You're done. You have
Yeah.
an equation of motion. You can't
This
do
is-
that
this is
in
why
Newtonian
learning-
mechanics. The other thing is
Yeah,
people
like-
are often muddled about what Newtonian mechanics is. F equals ma does not define force. It establishes a numerical equivalence between force and the mass of the accelerated mass. It tells you what force does. Force accelerates a mass. But it doesn't tell you what F is. If it's gravitational, F is minus gmm over r squared. And then you plug that in and you have a differential equation.
Yeah.
But you often have to use dimensional analysis or empirical fitting to figure out what F is.
Right.
And that's something that we don't spend any time on at all.
Yeah, we don't really think of those things, I think, because as you said, like the people that are teaching it have, I think, like understood it to be so fundamental that they don't even think, as we were talking about it, like they don't even think what it's like to learn from our end. So they're just like, oh yeah, F equals ma.
You know, the secret weapon of the theoretical physicists is dimensional analysis.
Yeah. Yeah.
Understanding the dimensional units that are being used in a quantity, you can establish a formula, a qualitative formula. It might be off by constants, but that's it. I mean, that's really an amazing thing, and we spend no time teaching people to do that.
Well, actually, I remember in our thermodynamics course, we did have we had to deal with dimensional analysis in the sense where they gave us a problem. I think we were dealing with like the shearing force, but like there's like a viscous liquid, something like that,
But that's
and we
more
had to
fluid
use
dynamics and thermodynamics.
right. It was all under the same umbrella of the larger like statistical mechanics, but we had to use just using dimensional analysis. We had to establish some proportionality between like
I remember
quantities
I
involved in
briefly
the problem.
remember that.
It
I
was
remember how important it was.
yeah, it was a very interesting problem because you had to boil it down to what was happening and think about, okay, there are molecules bouncing that have velocities, and there's a density, and there's a mass, and all these. And so you arrange these quantities together to get some kind of relationship, and all of a sudden, because the dimensions work out, it's a relationship.
Right. And so being able to come up with that, and another technique is order of magnitude estimation, which a lot of people don't really know how to do. And that gives you your first BS detector.
Yeah.
You know, so that gives you an order of magnitude, and you can look at the results you're getting and compare it to that and see if you have any hope of being in the right ballpark.
Right, we're very familiar with that, dealing with astronomical quantities. Yeah.
And in fact, I spent a lot of time doing astrophysics, as you mentioned. I've done gamma ray burst, power spectral densities. I've done neutron star models and things like that. So In
So-
fact, I with
yeah.
another MAST member and I actually solved the TOV equations for a neutron star, the Tolman-Oppenheimer-Volkov equation.
See, something like that. I just want to know. I really want to know if a professor, like, how do you know? First of all, I guess this is part one of the question. How do you know that no one else is working on the current problem that you are? Because you're just gonna do it anyways. Okay. Second question. I think this is a little more interesting. Because you're so interested in everything, how do you pick and choose what you actually research? Like, do you is it like, oh,
It's what grabs me. It's what grabs
Right.
me. I have like three
Is
or four
it-
things. Well, I'd like to do that, but this is really interesting.
Right. So is it often the case where you find a new thing to research, it grabs your attention, so you focus all of your time on it, and then maybe a little bit after that, something else grabs your attention, so you kind of push everything else to the side, so you don't really get much done in one singular topic?
I have a cabinet here, and I have like 20 research notebooks.
so you don't really go
And-
back and forth. You just
And
go.
I'll take a research
All
notebook
in.
out, and I'll do a page on it, and then I'll set it aside. And if I get grabbed by something, of course, then I'll have 15 or 20 pages done, and then I'll put it aside. But, you know,
Yeah.
to give you one thing, I got hooked into doing a research that I didn't want to get into. But I was in my mid-30s. I'm now 61. And I was kind of depressed. I couldn't think of a good problem to work on. Another way of putting it is all the easy problems had been done. And
What do you do now? Right.
And my wife of that time, who passed away in 2000, said to me, okay, what's the hardest problem in physics? And I told her, you are not going to get me to work on quantum gravity. And she said, why not? And I said, the graveyards are filled with theorists who died on that hill. And she said, what makes it so hard? And that, of course, was the fateful answer. And I had to explain to her how general relativity works and how quantum mechanics works, and the two shall never meet. Because, you know, basically it comes down to, in general relativity, you have a grid, and you know exactly where things are and exactly when they are and how fast they're moving. You have the energy momentum tensor, and then you have and that's equal to the curvature tensor, right? So you can't do that in quantum mechanics because you have conjugate variables. Energy, position and momentum are conjugate variables. Energy and time are conjugate variables. Angular orientation and angular momentum are conjugate variables. So if you know one, you can't know the other. And position and momentum are conjugate variables, so you can't do general relativity in quantum mechanics. And so she began progressing, and she would come up with a bunch of things all the time about ways of tackling the problem. And at first it was like, no, that won't work because of this. And it took me no time to think of what was wrong with it. And eventually, she, being very clever, she started coming up with more complicated things that I couldn't just brush aside. Then it might take me 5 or 10 minutes to think of a reason why it wasn't going to work. Now, I'd been reading a book on topology, and she asked me a question. To this day, I can't remember what the question was. She came up with this idea, and I said, no, that won't work. And then I remember hearing an audible click in my head, which probably means I have a brain tumor or something like that. And I thought, that won't work, but what about this? And I had a revelation. Now, we know that right now we only have one good theory of gravity, and that's general relativity.
Right.
And we're trying to unify gravity with the other forces. I don't know if that's possible, because gravity does things that none of the other forces do. Right? If gravity is the curvature of space-time around an energy density, a mass energy density, then effectively space-time is measuring that mass energy density, right, by its curvature. So in a sense, without taking consciousness into it, because I think that that makes me itch every time people talk about that, space-time is acting like an observer.
Yeah.
So space-time can't know where an electron is or its momentum any better than anybody else can. So maybe a way of doing quantum gravity would be, all right, let's look at these uncertainties, and instead of going from point to point, we go from ellipsoid to ellipsoid. I actually found a mathematical structure that does it. It's called a probabilistic metric space. Locally it's discrete, but globally it's Euclidean. And of course, using the Cartan process in differential geometry, you can always transform a Euclidean geometry into a Riemannian geometry. So that's one of the things that I'm working on.
Wow. And is this is a current thing that you're thinking about?
No, this is one of the things that I'm thinking of. But
One of the things. Are there like a list of like a top 5 that you have that you're working on right now?
right now I'm doing a lot of educational stuff, and that's taking a lot of my time. I'm maintaining the MAST website. We have a lot of free resources on there. I'm converting a lot of Mathematica notebooks to HTML, which it does intrinsically, so that's nice. I don't have to write all the code. Mathematica will handle a lot of that.
That's nice. That's actually.
But, so we're a Mathematica shop. In fact, Wolfram Research has given us 6 Mathematica licenses, professional Mathematica licenses, that they update for us every year.
Wow.
That definitely helps.
Wow.
That definitely helps. So I guess maybe I guess maybe right now, maybe right now you're more in the educational theme, right? So maybe
It's just that
also,
it takes a lot of time and focus to do that, and sometimes it's difficult for me to find the time. I now own a house. There are house repairs that have to be made. Things,
life.
life. Yeah, it's all.
Right.
Real life is what happens when you're not doing anything else, right?
Right, exactly.
And so, every Saturday afternoon we have a research session for MAST where we're about to start going through a book called Perfect Form, which is about variational methods in elementary physics, and we're going to be doing the problem set for MAST members, and that'll be...
Sorry, so when you say we, like, I understand that you're...
MAST who participate in that meeting will get together and work these problems.
No, but these are just like, because I know MAST, it also has like learners, right? Not them, just like the teachers almost. Is that what you would say? Or like everybody part of the organization, everybody's allowed. Okay. Can anybody be involved? Because I'm sure some of our listeners might actually want to.
Severe, we charge $10 a year.
I was actually getting
or
like,
$100 for life membership.
Wonderful. Okay.
And our website is www.madscitech.org. It used to be Madison Area Science and Technology, and we didn't want to change the website when we changed our name, but it's now Midwest Area Science and Technology, or we just call it MAST.
Right. Yeah, so don't worry. We'll put the link in the description below for anyone who wants to check the website out. If you want to look at that, not to worry. Yeah, because I'm actually pretty interested in how you started this in the first place? Like maybe take it to the mad part of it when not in the Midwest. Why, if you were already doing research, why start this? I don't know why.
Been interested. I never believed that I was unique. I've always met people who were interested in science, but they had the feeling that it was impossible without a degree. And I know
Exactly.
that it's not.
Proof, living proof.
And so I found people who were interested in pursuing it on their own. You know, some of them
Was that
have
just like a
degrees,
forum
some of
online?
them don't, but you know, that doesn't matter. We don't care what people's credentials are.
So
Now-
the ones that have degrees. Oh, sorry.
Now we are
wanna continue?
we don't take ourselves too seriously. I mean, you may have gotten that impression that I like to tell
Right.
jokes about myself all the time. But you know, it's like, oh, I have a point, but if I comb my hair the right way, it doesn't show. But you know, but we take the material very seriously. We don't allow. We get very uptight with loosely presented material. We expect people to nail these things down solidly before they present them. And if they're not nailed down, we will nail it down for them.
So, what kind of presentations are you? Because I know you were talking about your presentations, but I'm curious to know, like, because you mentioned some of them have degrees, some of them don't. So are there like different calipers, like different levels of presentation?
My wife has given talks about spreadsheet programs that she's used. My wife is also an amazing Mathematica programmer. She actually
Really?
wrote a Mathematica program that duplicates a piano. So you press buttons and it plays music.
Very cool.
A
Very cool.
Mathematica program. That's interesting.
You know, Mathematica is a generic programming language. You can do
Right.
just about anything in it, but you know, we had one guy who was a database programmer. He's since passed away, but he would give us talks about how to use the database system in Mathematica and stuff like that. So it isn't just math and
okay.
physics.
Yeah,
I
it's
also
a lot of things.
have a 10-lesson course on advanced severe weather spotter training, so if people want to go storm chasing with us, they have to go through that. But I'm a sneaky SOB. My wife has anxiety and depression disorder, and I don't necessarily mean to post that on the internet, but she has trouble with coping with technical terms sometimes, and one of our members was taking the course as a review, which you have to do every 5 years. And I was basically having Di sit in on it while we were doing this, and then I always give a final exam, and people get a chance to choose what kind of exam they want. They can have an oral, 1 hour timed oral exam, they can have a 1 hour written timed exam, or they can have a 3-day take-home exam. Of the 100 people who've gone through the severe weather spotter course, 2 people have done the take-home exam. Because I assume you have full access to the internet and books and even people like me, so I make it so that you're going to need that. You know, if you do a take-home exam, it's a research program. You know, like for
Wow.
example, I'll say, find a spotter location and develop a range card for it. You know, where you draw a map and you establish the distance from that point to landmarks in the area, so that if you see a tornado in there, you know how far away it is.
Oh, so I'm sure there's a whole process.
Yeah,
to go
that
with
is a full
tornado
project.
catching. Like I have no idea how that even
And
starts.
so, you know, but, you know, I was also a faculty member of Henley Putnam University for a period of time, which is basically a spook school, if you know what that means.
Not really.
An intelligence school.
Okay. So like smart people go there is what you're saying? I have no idea.
At this spook school for a time, and I did the same thing with my students there. I gave them the choice what kind, and every exam I wrote by hand, and it was different for every student.
Wow.
What?
Wow.
That seems overly excessive. I've never seen a professor put so much work into a class ever.
I taught the course through homework. That's how I would teach people. And, you know, I would recognize you have this weakness and we have to shore that up. And things like that. That's how I knew.
So how many students? How many students would you be teaching?
The most I had was 10.
Okay, so you didn't have to, you know, look after 70 students, you know, and write 70 different exams.
Just like when I was at Madison and we had 300 people in Physics 202. You know. Yeah. Just to get an idea of. I personally think those warehouse courses suck anyways.
Well, I mean, hopefully you taught, I'm sure you definitely inspired some people in that class. I mean, if I were to see my professor putting this much work into my class, I feel like I would automatically get, you know, more inclined to do it, because usually it's the opposite.
I had a really good, you know, sort of drifting into forbidden topics briefly, but I actually had a really nice feedback from one of my students who had been a Marine Scout sniper who was going through the course, and one of the courses I taught was Weapons and Weapon Systems, which was a tactics course. And he said you could tell that the person who taught this was a sniper.
Really? Just from the way they answer the questions and whatnot?
We had wargaming examples, and he was able to tell from the wargame. Basically, one of the wargame scenarios was a sniper hunt. And they could tell that the person who designed it was a sniper. So.
Right, because when you have that kind of training, it's just the way you think is just molded by that training. So you can immediately recognize when somebody else has been through the same.
You know, that's some really powerful stuff. I feel like, I mean, you just talking a little bit about, you know, just that attitude that the military gave you, just being in there. And I mean, look at, it just amplified it. Okay. It just amplified it a little bit, maybe you would say.
Honed in.
Yeah. Okay.
Right.
Yeah, that's a nice way to put it.
To realize, I mean, yes, I've had a talent in intellectual capability and in mathematical capability since I was a child, but I've been able to turn it into a skill. And that somebody who has talent has to be very careful not to rest on their talent, because talent can only take you so far.
How do you know that you have that talent, though? Because I feel like a lot of people sometimes don't even realize. Because you have it in physics. Someone might have it in, I don't know, cooking or something. I don't know. But, like, how do you realize?
You know, I mean, I don't know how to answer that question other than to interrogate somebody. You know, I mean, you can tell if somebody is bright. You can tell if somebody is able to do pattern matching. You can tell if somebody has critical thinking skill, and that's a skill. If anybody wants to boil it down to one thing that makes a successful scientist, it's critical thinking. If you don't have critical thinking, you're going to be open to every stray breeze that comes along. Everything, you know, the world is filled with great ideas that are crap. You know,
I would really love to know how you, I mean, I'm assuming, again, you already had a little bit of that talent that I'm sure, you know, pushed your creativeness. But for a lot of other people that are out there, a lot of people listening to this podcast right now that are probably like, oh, I think I'm talented, but what if I want to actually pursue this? Is there anything that you want to say to them? Is there anything that you want to, like, way to practice.
Asking yourself, how did the magician do that trick, and figuring it out.
That's the best way. I hate doing that because it's so hard to figure out. Because whenever I do, I just can't figure it out.
But if you can talk to somebody and understand what they're saying, or if you talk to somebody and you go and you start asking questions, well, what about this and what about that? That's leading towards critical thinking. You question everything. You never accept argument by authority.
Yeah.
And you don't just accept an idea because you like it. You know, you have
That's
to.
an important one.
Here's an important thing that I learned in the intelligence business, and again, this isn't breaking any rules. In every intelligence report, it's required by law that you write an appendix that includes what could be wrong with this analysis. It's required by law.
Wow.
That you attack your bias.
Wow. So even bringing that kind of critical eye to your own work is...
Absolutely. You have to be more critical of your work than you are of anybody else's, because you know what you're trying to do. It's like with this book, you know, as an example, we had been through it 5 times. We no longer saw the typos.
Yeah.
We couldn't see the errors. That's why we have an editor.
Right.
Yeah.
Exactly.
And even past that, I still get emails saying I found an error on this page. You know.
Right.
Yeah. I kind of had...
When I have a situation where I'm in front of a class and I write 10 equations on the board, I could go through every person's notebook and I guarantee you that every single one of them made a mistake somewhere.
Right.
Because people are so busy copying things down, they're not listening. You know, I love Ray D'Inverno's comment about course notes. A lecture is a way of getting the instructor's course notes into the student's notebook, often without interaction by the student.
That's basically what lectures are these days, right?
I mean, lecture is the absolute worst way to teach, because it lulls people into a false sense of security. I'm sitting here, I understand all that. 10 minutes later, you ask them what was your favorite part of it, and they go, what?
So would you rate like seminars? Are you saying like colloquiums or something like that is better, or what's a better way for you to teach? Right. I guess a seminar is basically So what would you say is a better way to teach or a better way to learn?
The best way to learn is probably the way I did it.
Just books.
Well, I mean, or by whatever mean. I mean, I would sit and talk to professors, and we would work things out on the blackboard too. You know,
so if you... Right, like if you were, let's say, 15 in the year 2022, how would you take up your education journey?
It would be a lot easier than it was when I was 12. I mean, because there's this.
Yeah.
I wish I'd had this book when I started out. But, I mean, the Feynman lectures were perfectly fine, especially with the exercise books.
Right.
And then I had several experiences, like the professors that I talked to were very open. They were very welcoming. There were a couple of curmudgeons who said, "Get out of my office." And I said, "Okay."
And you just moved on.
Moved on to the next office, you know. But I, in the astronomy department, I had a mentor. His name was Arthur Code. At that time, he was the chair. And when he was no longer able to answer my questions about black holes, he sent me to see Charlie Gable of the physics department, and he became my mentor and lifelong friend. In fact, in 1996, I was able to help him with a problem, and from that moment forward, I could die happy. He was struggling
Wow, you
with
helped him on a problem?
he was struggling with a problem, and I told him how to prove the theorem that he was trying to prove. He
Wow.
said that won't work, and I said let's give it a try. And we basically used mathematical induction. We tried it for the problem where n equals 1, and then we did it for if n then n plus 1, and it worked. And he thanked me, and at that moment I could die
Wow.
happy.
Wow.
What a moment. What a moment. I can't even. Because do you feel as if they ever had, and obviously this is just from you judging their body language, ever had like a moment of, oh, look at this guy who doesn't even, like, I have a PhD, and this guy that doesn't even have a degree is challenging me, or no one was like that? Right, you were mentioning that. Yeah.
Because I didn't go to talk to people until I had questions, and I had exhausted all of my resources. I mean, I didn't go up to them and say, what about this stupid idea? Although I had stupid ideas. I didn't realize it at the time. But I found out this is dumb. I remember the first tensor problem I ever worked was figuring out the components of the electromagnetic field tensor and then writing Maxwell's equations in those terms. And I struggled with that for a week. I was 15 years old.
Jeez.
Now I can do it in 10 minutes. But
So what kind of questions would you present to these professors? Because I feel like today, I don't know, because when you were telling your story, I just feel like if I were to go to a professor, like they would just be either like really busy or I would just not have a good enough question. So like what? Yeah.
my first question would be, do you have like 15 or 20 minutes?
Right.
And then I would ask a question. And
Now, were these questions like base, like, level of question and stuff?
So, for example, this was actually when I was in the physics department and helping teach a course on mechanics to juniors. And we were looking at the the energy momentum theorem. Now, like, how do you derive the energy momentum theorem from first principles? I know how it's normally done, where you go backward from the energy momentum theorem and go back and reverse the process and get to the force, and then you flip it around and present it that way, which is how most textbooks do it. So yes, you can prove this theorem, but there's no way that a student is going to be able to derive that. And it took me a week to figure out that the trick is integrating the derivative. Just like you do with Lagrangian, right? With the Lagrangian mechanics. So I'm like, this is a great teaching moment. You could teach students this trick on this relatively easy case, and then they'll use it the rest of their lives. But that's an example of the kind of question I would ask, and we would sit there and play with it for the next 15 or 20 minutes. Sometimes we'd come up with an answer, sometimes we wouldn't, but things would continue. And I had a clue from that moment how to proceed on my own.
I feel like you might have also, or maybe it's not, but I don't know if like your professors that you spoke to were definitely definitely helped you, right? Would you say that they like almost shaped your, interest and passion? Like without them, you wouldn't be able to do it?
I don't know that I would say that. I mean, I was interested in black holes when I went to Charlie. He didn't
Right.
He didn't shape my interest in black holes. But he certainly got my thinking more on track.
More on track. I think that's a good way to put it. Because I feel like if you're doing things by yourself, the on track part of it might be like, because I feel like if you're just doing.
But these days we have email, we have video conferencing.
Well. Right.
We didn't have that when I was a kid. We didn't have that when I was 15. I would have to physically walk to the university to go to their offices and talk to people in meteorology or astronomy or physics or biochemistry or whatever I was interested in at that time. But
Wow.
the other thing is you have to be willing to put yourself out there.
Yeah. Yeah, totally.
You know, you have a lot of the trap that a lot of people fall into is they live in an echo chamber of their own thoughts.
Mm-hmm.
And they never test their thoughts to against other people. So they don't realize that they're falling into this black hole. And they don't have the critical thinking to look at their own, to evaluate their own work.
Mm.
Somewhere along the line, our school maybe it never did, but our school system doesn't teach people to think. It tries to teach people what to think.
Mm.
But it doesn't teach them how to do it. There are, you know, I found like 15 questions that you can ask yourself. A checklist, if you like, and go through. Like, when you encounter a term, can you really define it? Even,
Right.
you know, there are going to be undefined terms where you end up with circular reasoning. Like, the whole thing with force and mass, it's a circular definition. You can't describe mass without describing force, and you can't describe force without describing mass. You just have to agree to understand sort of what you vaguely mean by those things. And what's energy? Nobody can answer that.
Exactly. It's just a number.
You do something, it's the same number when you're done.
Yeah.
Essentially.
And that's
right.
about it. You know, but it's the basis of all of physics, right? You know, so... but we don't know what the hell it is.
Yeah. It's I think energy is one of the funniest things that I try to grapple with, because no matter what I think about, right? Like kinetic, potential, friction and heat and all this stuff, it all boils down to, oh, it's a number. And, you know, if you have like, if it's a closed system, it stays the same. If you have like influences from the outside, it can change. That's about it.
There's some interesting insights you can get, like all energy is a volume.
Wait, all energy is a volume?
What's kinetic energy? mv squared, 1/2 mv squared. So mv squared, that's a volume, right?
Wait, what?
You mean like units of meter
Units
cube?
of
Like,
meter?
You have mass, you have velocity, and you have velocity. That's a volume. That creates a volume, right?
Okay, so in like a volume in like an arbitrary like units kind of sense.
Oh.
Same thing with potential energy, right? mg.
Right.
GH, right. That's a very interesting way to think about it. I have never thought of it like the individual. What? That's interesting. I've never thought about like the individual. I've never ever heard anybody say energy is a volume and describe it in the way that you just did. That's very
that is very interesting.
By the way, for those listeners out there, when he was talking about MV and V, he was kind of making like the right hand rule kind of look basically like the three axes.
Yeah.
I didn't know that.
Left-handed coordinate systems too.
Yeah. Yeah.
That is wow.
I'm still thinking about that volume thing. Like that's so.
Realized that it was like it can't. You know, not that it necessarily means anything, but it's just an interesting fact.
Yeah, it's like it's like a cube, but just like instead of distance, it's like mass
and velocity.
And if you think about it, it makes sense. If you integrate over energy, you're basically integrating over a volume.
Wait a second.
Wait, what?
If you integrate over energy, like integral of EdV, is that what
Think
we
of the
said?
energy that you're integrating, the differential of the energy that you're integrating over.
Oh, yeah, yeah.
Effectively works like a volume.
That's right. Because imagine you're integrating just like over the domain of like a cube, right? You have like dx, dy, and dz. But instead of the domain being distance, it's mass,
Oh, so you're
velocity,
literally
and so you
saying, like,
integrate
we're-
over like the differential is just it's just a variable at the end of the day, so it doesn't matter what it represents.
I mean, you gotta,
Uh,
don't get so, don't drive yourself into a rut.
Right, right.
Yeah.
Wow. Oh my. I have
Very
learned
cool.
so much today.
Wow.
Just mainly just about just living, I think. No, like seriously, just about living life, because I feel like your outlook on life and the way that you tackle things, oh, I like it so I do it. That's such an amazing way to live.
With my handicap, it's the same way. In 2018, I lost my left leg below the knee from an infection I got. And then September, that was in May to June. And then in September, I went blind. I got severe cataracts in both eyes.
Oh my.
Wow.
And then my mother-in-law passed away. It was a bad year. And fortunately, we had the resources that I was able to get cataract surgery on both eyes. And but the least thing that happened was my leg went.
Yeah. Oh
But
my.
Through
It
all
hasn't
that.
stopped
Through all
me.
that. Right. Exactly. Exactly. That's exactly the takeaway from here. Through all that.
I mean, yeah, I miss taking long walks, but it hasn't really changed the way I do things.
Right. Right.
Wow.
Wow.
I'm
Well-
still like just thrown aback by all
Yeah,
the stuff you
just-
do. I think definitely gonna talk about it.
There's
Okay,
just
I think
so much content.
there's so much. I feel like, absolutely,
Yeah.
that would be.
on
Yeah.
Meetup.
So once again. Okay, so once again, give us the link or whatever to the website and whatever has a schedule, and we'll be putting everything in the description below. So all the listeners out there, I legitimately think this sounds really cool, and if the timing obviously works, I'm not sure. I think it's just central, right? So just an hour behind, not horrible. But if the timing works out, I think that will be amazing. Hope other people can join as well. I mean, like if you just have a passion, we have a lot of listeners that just like physics but are not in physics, exactly like you. So
We have no entry requirements other than you're interested and you're willing to learn.
that's exactly what you want. That's all you want. This is almost like a school. I mean, I'm assuming that's how you structured it, right? It's like a university,
We charge $10 a year.
which is
Yeah.
just a little less than than actual university. Just a little bit. So I think that's definitely an advantage.
Quality of education
Right.
you get is pretty good.
Yeah. Okay. That's good. That's good to hear. And I mean, we've already spoken about we have episodes and episodes on how to learn physics, how to learn math. Like we give out all like Feynman. Like for example, we were mentioning the Feynman lectures that are literally available for free online. So many resources, books, and whatnot that even you were able to do. So I'm sure
I actually met Feynman at a conference once.
Wow.
that is absolutely
Wow.
insane. Like the fact that you met Richard Feynman.
Wow.
We didn't really talk much about physics. He was telling the story about how he found the fence at the hole in the fence at Los Alamos.
Wait, what?
The hole in the fence.
At Los Alamos for the Manhattan Project, he found a hole in the fence. And did he go and talk to the security people and tell them that he found a hole in the fence? No, he didn't do that. He went in the hole and walked out the main gate, and then he went in the hole and walked out the main gate, went in the hole, and then he got arrested walking out the main gate again because they...
What? What? That's hilarious. Hilarious. That's hilarious.
That's hilarious.
Well,
man.
who would have a character? I'm sure I would. That would be awesome.
Yeah.
But if anything, should be taken away from this podcast, I feel like it's literally just do what you want to do what you love,
and have the courage of your convictions. The worst that somebody's going to say to you is no.
Best way to put it. That's the worst.
And, when I called John Wheeler Collect, I showed you Gravitation. He was one of the co-authors of that book. He was probably the greatest physicist you've never heard of.
John Wheeler's a big name, of course.
And he was a really sweet guy. And, in fact, just before he passed away, I reminded him of the phone call that we had. And he really appreciated that. But I called him when he was at University of Austin Collect in 1974.
Wow.
Wow. Collect call. Oh my.
We talked for 45 minutes about black holes. I was 13 years old at the time, and he sent me a mimeographed copy of the bibliography that he gave to his grad students.
Wow.
How could he speak to a 13-year-old? I feel like that really shows a lot about even them as a professor. Because I feel like, I just felt like they wouldn't, really. He couldn't tell from the voice. I feel like a 13-year-old voice would be quite distinctive.
When you've dealt with a couple of hundred students.
Oh, yeah.
Yeah, that's also true. That's probably,
true.
You can't really assume much. Yeah, you're totally right. You're totally right.
Yeah.
Wow, that's just amazing. That's just amazing.
That was literally one of the formative experiences for me.
Mm-hmm.
And I pursued that bibliography, and I got copies of all the papers and read them, and worked through gravitation. I had a great moment. I was going to solve the vorticity equation of fluid dynamics using the stress tensor. And I figured that would be great. And I suddenly realized at that moment, 15 years old, that it didn't matter how big our computers were, we were never going to be able to forecast the atmosphere correctly because there was no way that we could solve the vorticity equation. Because you need to know the friction coefficient of air. And the friction coefficient of air here is different than the friction coefficient of air here.
Right. Oh no.
Because the chemical composition of the air here is different than it is here.
Exactly.
Right.
So without being able to know the friction coefficient of air, you can't solve the vorticity equation. So everything is approximate.
Can we do it? Can we do it now? Well, now we can do it, right?
No.
Oh, I thought
There's this dense throughout the atmosphere.
But well, an approximation is, all that we do, right? That's how we do all of
We
our
don't
methods.
even know if the Navier-Stokes equations are the correct equations.
Well, they're pretty good. it's kind of funny that you mentioned that because I'm literally doing my research on that right now. So
They're good out to 36 hours, and then you're dropping off to background. Then you're dropping off to statistics. 48 hours, and you've got a 60% accuracy rate in forecasts.
So you're talking about atmospheric, right? Navier-Stokes would definitely not be essential for atmospheric. I can definitely see. I'm assuming Navier is more for like immediate.
It's the best equation we've got. But I mean, look at the Millennium Problem, right? We don't know if it's solvable everywhere.
Right, exactly. Yeah, that's the big problem.
So, that's one of my areas of research, too, because I do tornado physics. And I also do... when I was in Madison, I was part of the Chaos and Complex Systems seminar group, for example. I gave many talks to them about the geometry of chaos and things like that.
That's quite an enlightening thought to have at 15 years old, to realize that, you know what? Everything is an approximation.
I don't even know if I knew the word approximation.
It doesn't matter how powerful your computer gets.
Yeah, no matter what.
You're never going to be able to accurately forecast. Of course, there is one way you could do it. You could build an Earth and an atmosphere and run the atmosphere as a model of the atmosphere.
Yeah, well, I'm assuming that's not very feasible.
No, but that's what it would take. I mean, we don't even know how many degrees of freedom there are in the atmosphere, right? The volume of phase space could be Avogadro's number times the number of particles, right?
Yeah. Yeah.
Massive, yeah, I guess it could be. We don't even have a way to estimate that.
So yeah, the computational power would be, unimaginable.
Well, quantum computers, here we come.
Well, even a quantum computer might not be
Yeah,
able
no,
to
it wouldn't
do
really
that.
solve it. No, because
I mean, the nice thing about
same
it is you
problem
can do matrix
holds.
operations in a single step. That's the big advantage that a quantum computer would have.
I mean, it definitely does help with certain programs. I mean, there are actually still till date so many programs that run much faster on supercomputers than quantum computers.
I've actually built a quantum computing simulator in Mathematica.
How? What? How is that even done? How can you? What?
It simulates the quantum computer. It gives you the results that a quantum computer would give you. It takes forever by comparison, but
Okay.
it simulates what a
Damn.
quantum computer would be able to do. Basically, it's operator algebra stuff.
Wow.
Wow.
Very enlightening experience for both of us
Yeah.
today.
God.
Wow.
Well,
We've learned
we've
a
covered
lot.
a lot of ground in this
have.
podcast.
We have.
Super interesting episode. Thank you so much for contacting us and making this episode happen. It's greatly appreciated.
Sure, I had a blast.
I'm gonna be completely honest. I read Amateur Scientist on your website, and I saw a bunch of things that you were doing, and I'm like, okay, I mean, I'm sure like he's interested in this, but I'm like, we're probably just gonna talk about that. And I also saw you had a few books here and there, so I'm like, okay, he writes in his free time. No way would I have imagined that you actually write research papers as an amateur scientist. So there are a lot of things that I think I have definitely learned today. First off, you don't need school to do what you want to do. I think that's the big takeaway. And second of all, even if you are in it, okay, let me actually ask you this, like a nice end off. Do you have anything to say that to people who are already in school? Because I feel like a majority of our listeners probably are and are already taking physics or something like that. Is there anything you want to say to them to how to get that extra bit of learning, or how to satisfy yourself and not just do what the school is telling you to do?
I guess I would. There are three things that I would say. First thing is, as I said in this discussion before we started, one thing I tell all of my students: fail early and often. You never learn by being right. All you learned is that you knew it in advance. You only learn by being wrong.
Exactly.
Second thing, and this is also something that I give my students, you can either be smart and look stupid, or you can look smart and be stupid. If you have one of the lessons I learned from the Navy is the only stupid question is the one you don't ask. If you have a question, ask it. Otherwise, you're being stupid.
Yeah.
And
I agree. Totally.
So often we're content with being familiar with an idea rather than really grasping it. The third thing I would say is, while we have to write a book or present a series of lectures linearly, your brain doesn't work that way. There are going to be things that you grok immediately. There are going to be things that you will be able to parrot the definition of and won't understand for 10 years. Don't let that get in your way. Write down the fact that you didn't understand that and move on. And pretend like you did understand it. But be aware that you don't.
Some very important lessons here, I think, for everyone, including
Yeah.
and
So
very much
the
us as
first
well.
step is knowing that you don't know it.
Yeah.
right? If you're just blind to that fact, then nothing's ever going to change.
Yeah. Wow. So, I mean, I hope to everyone listening out there, I mean, we definitely did, and I'm sure if you're listening till right now, you definitely enjoyed this podcast. So, thank you, George, first of all. As Parker already mentioned, thank you so much for this conversation. We've never expected it to happen. So happy that it did. So thank you for that.
I have a
Yeah.
tendency to follow through on things when I start them.
Well, here we are. So we're going to put all the links to everything in the description if you're interested. And make sure to follow the podcast for more episodes like this one, and to rate the podcast 5 stars on Spotify.
Is there anywhere that you want, apart from the link in the description that we're already going to put, is there anything else that you want to just share with the listeners out there?
I have been considering launching a podcast of my own, but I haven't taken the step yet. So we're still exploring the idea, what would we cover and things like that. But but I've been listening to you guys, and that's sort of been inspiring to me.
Awesome. So
We've inspired you.
keep
my God.
everybody out there, keep your eyes and ears open for George's upcoming podcast, possibly.
That would be really cool. That would be really cool.
All right. Well, I guess that's it for the episode. It's been episode number 108
That's the one.
of the Math and Physics podcast. So, I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.
Thank you.